So in this problem, we will try to predict the products of reaction based on the combination of reactants given in the question. And obviously, as we know, for a substitution reaction, we need a substrate and we need a nucleophile. So for the combination of reactants that are given here, we need to make sure we understand which one is a substrate and which one is a nucleophile. And table 6.1 shows you all the nucleophiles that can be used in these questions that you see here. So paramethyl benzyl chloride is going to be an aromatic ring containing molecule, and there is a methyl on the para position, and this is the benzyl chloride because the phenyl ring with a CH2 is a benzyl group, and that is going to react with sodium acetylide. So acetylide is carbon with a negative charge like that, so it's an alkyne, and acetylide is the anionic conjugate anion of the alkyne. So sodium acetylide is Na+. So this is the nucleophile and that is the substrate, and the chlorine is the leaving group. So the electrons are going to be donated to the carbon here from the acetylide, and the chlorine is going to leave, and therefore the product is going to be the benzyl group with now the alkyne unit attached to it, acetylene unit attached to it. So that is the product of this reaction. So you can definitely expect to see questions of this nature in your quizzes and tests, where you are given the names of the compounds as opposed to just the structures themselves. So make sure you follow table 6.1 to see what all the nucleophiles you can have, and also make sure you go back to naming in the earlier chapters to know what the structure of the reactants are in your questions. Okay, so the second problem that we can pick up is 1,6-dibromohexane. So 2, 3, 4, 5, 6, that's hexane, and you have 1,3-dibromo. So you have bromine on the first carbon and 1,6-dibromo, bromine on the second carbon. And here you're using sodium cyanide, which is Na+, Cn-, and you're using excess sodium cyanide, which means the cyanide is going to react with both carbons and let both the bromines leave. Therefore you're going to get a dicyano compound. Cyano. So that's also a triple bond. Remember, we can just write a Cn, or we can just write a carbon with a triple bond to the nitrogen. Both of these are equally correct. So that is a product of the reaction there. And 1-methyl-1-chlorohexane reacting with water. So that is the substrate, and this reacting with water. So water here is the nucleophile, and the product is going to be, so this is a neutral nucleophile, remember, therefore you're going to have an OH, not an OH2. That is not the right answer. And so one of the hydrogens is going to be kicked out as H+, and you'll be getting HCl as the byproduct of this reaction. And if you want to write an oxygen with 2 hydrogens, then you need to make sure you have a positive charge. And also remember, in the mechanism, this is not the final product, it is still an intermediate in the reaction, and that is going to kick out an H+, and you get the alcohol, and the H+ goes with the Cl-, which is the leaving group, to give you HCl. So this is an intermediate, not the final product, therefore you have to make sure that you give the neutral product as the product of this reaction. Okay, and we can also look into problem B. So N-propyl bromide. So propyl bromide is this, and N represents the straight chain compound as opposed to the bromine on the second position. So if we have the bromine here, that is going to be an isopropyl bromide or 2-bromopropane. So this is N-propyl bromide is this structure, and that reacts with sodium cyanide. Therefore the product is going to be simply that. Okay, and we can also try F. Tertiary butyl bromide is that, because this is the tertiary butyl group. So tertiary butyl bromide is this, and that reacts with ethanol, again a neutral nucleophile, and as you would know, the hydrogen is going to be removed and the product is now going to contain 2 alkyl units. And if this is, say, carbon 1, that is carbon 1, and if this is carbon A, that is carbon A, and the hydrogen gets kicked out as H plus, and that goes with the Br minus, so the byproduct is going to be your HBr. The next problem asks you to predict which alkyl halide and which nucleophile will give the products you look at here as the result of the reaction. So in this case, we again have to identify which new bond is made and which part of the molecule should come from the substrate and which should come from the nucleophile. So if we take, for example, A, it's an ether, so you have a CH3O CH2, which means this oxygen is going to make a bond on one side, and that is the side that will be the nucleophile. So as we discussed in the classroom, we can make this product from 2 combination of reactants. So you can have CH3O minus reacting with 1, 2, 3, 4. So it could be a bromide, a chloride, or an iodide, doesn't matter as long as you have the right carbon chain. So 1, 2, 3, 4, you have 4 carbon chains. So 1, 2, 3, 4, and if this is A, that is A. So this combination can give the product you're looking for. So if this is A, this is 1, 2, 3, and 4. So this combination of reactants can give the product, or you can also switch the oxygen to the 4 carbon chain and switch the leaving group to the 1 carbon unit. So we can also have that reacting with to give the same product here. Alright, the next problem we can focus on is making this alkyne here. So we have a propane, so let's call this 1, 2, and 3, and let's call this A and B. Can react with the acetylide anion, as you can see in table 6.1. So this anion could be a nucleophile, and this could be the substrate with the leaving group, and you can donate electrons to this to make the product you're looking for. So 3 carbon chains, so 1, 2, and 3, and carbon 1 is now going to have carbon A, which is going to be a triple bond. So this is carbon A, carbon B, 1, 2, and 3. So this combination is going to give you the product you're looking for here. And the reason why we choose this is because acetylide is a more stable anion, and that will be able to react with this carbon center, which contains the leaving group. And if you want to make benzyl cyanide, say for example here, CH2C triple bond N, then you want to use a benzyl bromide and sodium cyanide. So remember to include that CH2 over there. So that is the product you're looking for. That CH2 is, say for example, carbon A, and if this is B, that is carbon A, and this is carbon B, which donates electrons to the carbon so that the leaving group can leave. So this is the combination you want to use. So problem F is important in emphasizing an important concept in substitution reactions. So if you want to make this product, you might try to make this from 2 different set of reactants. So the one that would work is taking the oxygen along with the phenyl ring and reacting this with an ethyl bromide or bromoethane. So the countercation here could be a sodium, and these electrons can be donated to the carbon here, and the bromine can leave, giving you the product that you're looking at here. That is one combination. The other combination, similar to the approach we used in problem A, could be the bromine on the phenyl ring and the ethoxide being the nucleophile. Now this reaction will not work, okay, because here you're talking about a halogen on an sp2 carbon. So if you choose this substrate, I'm just going to use double bonds here. If you choose this as a substrate, that is not going to work because the leaving group is on an sp2 carbon. So a leaving group on an sp2 carbon is not going to be a good leaving group. In this case it worked because the leaving group in both combinations were on sp3 carbon. So if you look at this, CH3Br reacting with oxide, so the leaving group was on an sp3 carbon, and the other combination was N-butyl bromide reacting with the sodium ethoxide, and here also this was an sp3 carbon. Therefore both these combinations will work to give you the product you are expecting here, whereas this will work and this will not work.